The next kind of register we're going to look at is a serial register. When we looked at parallel registers, we knew that each of the flip-flops sampled one bit of the data stream. In a serial register, it's a little bit different because the output from one flip-flop is going to give us the input for the next one. So what we see here is a shifting of information from one flip-flop to the next flip-flop. Because of this, a serial register is also called a shift register. Let's take a look at one now. So here's the beginning of a serial register. We can see that this time we've got a JK flip-flop. We have a falling edge on our clock because of the bubble here, and we have this JK flip-flop hooked up to act like a D flip-flop. So we have our D input, our data. So our input is going to come one bit at a time now into here, and because it goes into J and inverted into K, this universal flip-flop is going to act like a D flip-flop. So let's mark in our falling edges. So we're going to sample here, 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 and here. Our D flip-flop is we're going to start low, and we're going to sample at each of these points. So we get a low here, a low, we get a high here, a low at this sample point, a high, and then a low again. So this is the value that we're going to see appearing on Q. We can see the low is reflected, the high, the low, the high. So we can see that information shifted just a little bit over. Now we're going to add a second flip-flop. So again, it's a JK flip-flop, falling edge device, and this time we've taken the output Q from the first flip-flop and Q0 and fed them into J and K. Now remember, Q and Q0 are the inverse of each other, so what we have here is another data flip-flop, or a D flip-flop, where we have a signal and its inverse being fed in. So what's going to happen? On the falling edge of the clock, this flip-flop is going to sample Q. So this is going to become our input waveform for our second flip-flop. So what's going to happen, we're going to assume it's low to start. We're going to come across, and what we're going to do is sample Q3 at this point. Q3 is low, so we're going to hold that low to the next sample point. Q3 is still low, so Q2 stays low. Our next sample point, Q3 is going high, but remember we have that bit of a propagation delay, so it isn't actually high at the sample time. So we're going to stay low one more time. Here we sample, and it's high going low, which means at the actual sample time it's still going to be high. So Q2 is going to go high. We sample here. We're going to take the starting edge, so it's a low. So our output's going to go low. And here, it started off high. Our output's going to go high. So what we can see here, and this is kind of interesting to look for, is we can see our pulses starting to shift. So if you think of that as an arrow, we can see that high we had here now appears 1 clock pulse later. There's our high, 1 clock pulse later. So now we've added 2 more flip-flops. So we have Q3, Q2, Q1, Q0. One input stream still. So each flip-flop is acting like a D flip-flop. Its input coming from either the data stream for the first one or the previous flip-flop for all subsequent ones. So we can see Q3 and Q2 are marked in from what we've done before. So what we need to do now is take a look at what Q1 is going to do. So Q1 is coming from here. So its input is going to be based on Q2. So we're going to sample Q2 at each of these points and base our output of Q1 on that. So we're going to stay low until over here, which is the first time we see a transition. Now remember, because of the propagation delay, it's still going to register a low here, so we're going to stay low for one more time period, at which point it'll go high. It's going to, at that point, sample a high, so it's going to stay high for this time period. Here, we're going to sample down here a low, and so it's going to go low at this point and stay low. So if we look at our traces again, we can see that pulse shift again. So that's why it's called a shift register. Now we have one more flip-flop to look at. So Q0 is going to be dependent on the waveform generated at Q1. So if we look down here, we're going to sample a low, a low, a low, low, a low again, because this change doesn't happen until just after the sample time. This one we're going to sample as a high, and so our output is going to stay low through here. And finally, there's the one where we sample a high, and Q0 is going to look like this. So we can see that pattern extends down into Q0. Now you may be wondering why we didn't see this positive edge on our D pulse. And that's because had we sampled here, we would have picked that up. But because we took our first sample at this falling edge, we didn't have a chance to capture that. If we had, we would have seen that shift down through the registers as well. So let's summarize what we've learned about a serial register. First thing is that it's also called a shift register. And the reason for that is because the data coming in on D, one bit at a time, is shifted from the leftmost register all the way through each one until each of those registers is full. So if we had 16 registers, it would take 16 individual bits coming into D for that register to be full. The important things to remember: we need one flip-flop for each bit of data we need to store. So if we have an 8-bit value, we need 8 flip-flops, and it's going to take us 8 clock pulses to get that value stored in those registers. Now, the storage itself is a sample and hold, and it's on a clock edge. In this particular case, it's a falling edge because of this bubble, but it could just as easily be a rising edge, so it's important to pay attention to that. Now, in the last register we looked at, we had the information coming into Q0, then going to Q1, 2, all the way up to Qn. In this case, the data comes into Qn first, and then goes down through and eventually ends up in Q0. Both of these are quite valid. One is a shift from the most significant bit down to the least significant bit. The other takes the data into the least significant bit and shifts it until it's all there in the most significant bit. Both are quite acceptable. It really just depends on the application and the order in which the data is being transmitted to you.